Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we were discussing about the consolidation phenomena, and we have derived the consolidation equation, the 1D consolidation equation, and the solution yields in the last lecture we have seen the solution yields this thing, this expression. So, equation 4.31 we have established in the last class, right, or the last lecture. So, basically in this, from this equation, I mean what you are getting the excess pore water pressure at any point of time and at any location along the depth of the or along the thickness of the deposit, right. So, and we introduce one new term, that is TV, that is the non-dimensional term, and that is equal to your CV into T divided by HDR square, right. So, where CV is nothing but your coefficient of consolidation, T is the time, and HDR is the half of the thickness of the deposit. Now, this time factor is very important parameter, we will see later on, I mean for calculation of your excess pore water pressure, and particularly to calculate the settlement and degree of consolidation and other things. Okay. So, this equation is my backbone equation, you can say, by which we can determine the excess pore water pressure due to 1D consolidation. Okay. So, once you know the excess pore water pressure and how it is getting dissipated, you can get other information like how your effective stress is getting enhanced and effective stress is getting built up, right. Now, because consolidation progresses by dissipation of excess pore water pressure, the degree of consolidation at a distance z at any time t is given by say u z, capital U z is the degree of consolidation. That means, I mean if I say my degree of consolidation is 100%, that means the soil is completely consolidated. Okay. So, it is a progressive process, right, I mean starting from t equal to 0. So, you are continuously, I mean with the same amount of say I mean increment of stress or the stress, total stress increment. So, you are getting gradually the dissipation of pore water pressure, excess pore water pressure, and you are getting enhancement in the effective stress. So, that is the progressive or the gradual process, right. So, in that process you need to know at any point of time or any point at any location, say z. Okay. So, I mean now you can recall that z is defined from the bottom of the layer of concern, and then basically at any depth, at any location z, if you want to find out what is my degree of consolidation, how much the consolidation happens. So, that thing basically will be obtained by this equation. So, what is u z, that is the degree of consolidation is nothing but u naught minus u z divided by u naught, right. So, where u naught is nothing but the initial excess pore water pressure and u z is nothing but the excess pore water pressure at time t. So, you are trying to find out the degree of consolidation at any depth, say z, and basically you find out u z, that is the excess pore water pressure at that location at any point of time t. Okay. So, once you know u z, that means that is the excess pore, because the u z will be of course your will be less than u naught, right, as the initial excess pore water pressure will be always higher and gradually it will be dissipating out, and that thing already we have seen. So, u naught minus u z. So, the initial whatever you had, and now at any point of time say t, whatever say excess pore water pressure you are having, that is u z, the difference between these two with respect to the initial excess pore water pressure will be giving you the degree of consolidation. Okay. So, this much will be the consolidation happen at any point of time. So, that is nothing but 1 minus u z by u naught. So, that equation is very important equation. So, we will see later on. So, equation 4.31, that means the equation what was giving me the excess pore water pressure in terms of say initial excess pore water pressure and say time factor and all those things, that is a fundamental equation. So, that equation 4.31 and just now whatever we have seen equation 4.32 can be combined to obtain the degree of consolidation at any depth z, am I right. So, now it can be combined to obtain the degree of consolidation, because the equation 4.31 will give me the information about the excess pore water pressure at any point of time at any depth z, and the equation 4.32 will give me the information about the degree of consolidation at any depth z at any point of time t, right. And if you combine these two equations, you will be getting the idea or getting the say information about the degree of consolidation at any depth z. Now, if you look at this problem, so basically along y axis we are plotting z by HDR, that is the normalized depth, okay, with respect to HDR, and along x axis you have degree of consolidation uz. Now, the what was the total depth of the what was the total thickness of the soil sample rather. So, that was twice HDR. So, that means basically z is varying from 0 to 2 HDR, right. So, that means the normalized factor z by HDR will be varying from 0 to 2. So, within that you have the soil or the clay deposit, saturated clay deposit. Now, if you recall that saturated clay deposit is getting sandwiched between two sand layers. On top of the clay layer you had the sand layer, and at the bottom of the clay layer you had one more sand layer, right. So, those sand layers are basically facilitating the drainage, right. So, in other way if you look at, so basically those along those surfaces, the interface between the clay layer and the sand layer at top as well as at the bottom, basically your pore water, excess pore water pressure will be immediately 0. That means, if you increase the load, okay, immediately you will be getting 100% consolidation, or the degree of consolidation will be 100% at those locations, am I right? Because that at that location, so this was the deposit, right. So, if you recall, this was your sand, and this was your sand, and this was your clay, which the layer which is a matter of concern, right. So, along these surfaces, and this is basically at that location your z by HDR was 2, and at that location z by HDR was equal to 0, right. So, this is varying from 0 to 2. Now, at these surfaces, basically at the interface between sand and clay layer, basically if you see that drainage is not a problem. So, if you load the soil, immediately the drainage will be happening. So, water will be expelled out at that location. So, that means once you are applying some excess pressure or the excess load, and immediately if water or the excess pore water pressure is getting dissipated, then the consolidation will be happening as 100%, am I right. So, at that location whatever excess or pressure or extra load or additional load you are applying, because of that you will be getting 100% consolidation always at these locations, right, because immediately water will be expelled out from the clay layer. Now, as you go deep and deep, so you have two different conditions. One is that as you move from say from this boundary to the middle of the layer, and as you increase the time. So, there are two things, one is the time, another one is the how you are getting the distribution of the excess pore water pressure. Now, for example, say if TV equal to 0.1, that is the time factor is 0.1 at some time, because TV is nothing but CV into T divided by HDR square, right. CV and HDR both are say for a particular deposit. So, that will be kind of constant, right. So, now basically at certain time what will happen. So, this will be your say at TV equal to 0.1 say, this will be your excess pore water pressure distribution or the degree of consolidation, the plot of degree of consolidation, right. Now, that degree of consolidation is nothing but it will give you the impression about the excess pore dissipation of excess pore water pressure. Now, what does it mean? See, if you see this curve will give you the degree of consolidation. Now, at Z by HDR is equal to 2, you are getting 100% degree of consolidation, that means uz equal to 1, right. Similarly, you will be getting uz equal to 1 at Z by HDR equal to 0, because water is immediately draining out. So, you will be getting the excess pore water pressure will be immediately becoming 0, and you will be getting 100% consolidation at those locations, as I told you. So, whatever may be the case, or whatever time you consider, right, or whatever say time factor you consider. So, always at the interfaces you will be having 100% consolidation, okay, degree of consolidation will be 100%. So, that is what the uz is equal to 1 at the interfaces. Now, as TV increases, right. So, this is the as TV increases, you are getting the higher degree of consolidation, right. But if you look at, as you are at the surface of the clay layer, that means surface of the clay layer means either on the top surface or on the bottom surface, your degree of consolidation is 100%. However, this degree of consolidation is reduced, right, at the, so at the middle you will be getting minimum degree of consolidation, right. So, at the middle you will be getting minimum degree of consolidation. So, at any point of time, if you look at the distribution of degree of consolidation along the depth, along the thickness of the layer. So, basically you will be getting the maximum degree of consolidation at the interfaces, that means at the drainage phase, okay, and you will be getting minimum degree of consolidation at the middle of the layer, because at the middle of the layer, if any water particles, if you consider, this water particle will take some time to go either on the top or towards the bottom say interface to drain out from the soil or the clay deposit, right, it will take some time. So, that is why the degree of consolidation will be minimum at the location, because degree of consolidation is directly related to the how the water is getting, or the excess pore water pressure how it is getting dissipated, right. So, as TV increases, your degree of consolidation is increasing, that you can say if you move in this direction as I showed by this arrow. So, if you move in this direction, as TV increases, that means as time increases, basically your degree of consolidation also increases, but at the same time your degree of consolidation will be maximum at the interfaces, but it will be minimum at the middle of the deposit, right, and gradually it is increasing, right. So, you have two different parameters, one is the time, another one is the thickness of the deposit, clay deposit, right. I hope that you have understood this thing. So, now this is the distribution. Now, in that way basically your degree of consolidation will be varying, as well as your excess pore water pressure will be also varying. Now, the average, now basically you have seen that degree of consolidation is varying with depth, right. So, degree of consolidation is not a constant for the whole deposit. So, if I consider this is my soil deposit or the clay deposit, saturated clay deposit, I cannot say my degree of consolidation is at a particular time, my degree of consolidation is constant for the whole deposit, no, right. Already we have seen it will be maximum at the boundaries and it will be minimum at the center of the deposit. So, we can think of some average kind of degree of consolidation, because I need that to talk about the degree of consolidation for a particular deposit. So, unless until you go for the real distribution, you always think about the average kind of degree of consolidation. What is the average degree of consolidation for that particular deposit? So, the average degree of consolidation for the entire depth of the clay layer at any time t can be written as U equal to SCT divided by SC. What is SCT? SCT is nothing but settlement of layer at time t, okay, and SC is nothing but the ultimate settlement of the layer from primary consolidation. Am I right? So, after at the end of the primary consolidation, what is the ultimate settlement? That means, when your degree of consolidation is 100%, at that time what is your ultimate settlement? So, that is the maximum settlement you can have from the primary consolidation. Now, SCT is in between, as time progresses you are getting higher settlement and slowly it will be equal to SC, right. So, SCT at any point of time, SCT divided by SC, this ratio will give you the degree of consolidation, which is nothing but 1 minus. Now, what is this? I mean, if you see the equation 4.32, so 1 minus u z by u naught, that was there, right. That means what is u z? U z is nothing but excess pore water pressure at time t, that is the average kind of excess pore water pressure for the whole depth. Say if I consider, then basically this expression, the numerator will give me this average kind of excess pore water pressure, right. So, that means u z into d z, u z is the excess pore water pressure at any depth z, okay, into d z, which is integrated over 0 to 2 HR. 2 HR means the total depth of the clay deposit you are considering. So, you are integrating over the whole thickness of the clay deposit divided by the 2 HDR will give you the average excess pore water pressure, right. So, at any time t divided by u naught is nothing but your degree of consolidation, right. If you come back from equation 4.32, this will be the expression, okay. So, now substitution of the expression for excess pore water pressure u z in equation 4.31, that is the fundamental equation whatever we have derived for 1D consolidation, then we will be getting the degree of consolidation, average degree of consolidation rather is u, capital U is equal to 1 minus m equal to 0 to infinity into 2 by m square, capital M square into e to the power minus m square T v. So, these terms capital M, T v, these terms already we have defined, right, and small m is already defined, that is some integer. Okay. So, if you know these things or if you put all these values, you will be getting the magnitude of average degree of consolidation at any point of time t. Okay. Now, the values of T v, that is the time factor, and their corresponding average degree of consolidation can be obtained as if u equal to, that is the average degree of consolidation, if it is 0 to 60%, then your T v can be obtained or T v can be calculated as pi by 4 into u in percentage, of course, divided by 100. Okay. Or if u, that is the average degree of consolidation, if u is greater than 60%, then T v will be calculated from this expression. Okay. So, that means if you know the degree of average degree of consolidation capital U, then you can calculate T v, that is the time factor. So, once you know T v, you can find out other parameters. When we will be taking some numerical problems, you will appreciate that how these equations are getting used. Okay. Now, the coefficient of consolidation C v, because that is another important term. So, C v you can remember, I hope you can remember, right. The coefficient of consolidation C v generally decreases, because I need to find out coefficient of consolidation, right. So, if I know the coefficient of consolidation, then other parameters I can find out. So, how to obtain coefficient of consolidation from your consolidation curve or the E log sigma prime curve. So, that is nothing by my consolidation curve. How I will get the coefficient of consolidation from the consolidation curve. So, let us find out that. So, before that, the coefficient of consolidation C v generally decreases as the liquid limit of soil increases. So, this is true for any kind of say plastic soil, that means clay type of soil. So, generally it decreases, C v generally decreases as the liquid limit of soil increases. Okay. So, anyway, so there are now two methods by which you can find out the coefficient of consolidation C v. One is the logarithmic of time method, another one is the square root of time method. Now, first one I will discuss. So, logarithmic of time method, what is that? Now, in the consolidation curve, basically extend the straight line portions of primary and secondary consolidation to intersect at A, right. So, you might remember you have say E log sigma prime curve. So, basically you are getting something like that, right. So, basically what it says, this is your primary part and this is your secondary part, you extend this part and this is the point say A.